So go ahead and get that packet out. I just want to go through some with you. Just to kind of help you get started on some, because I know some of these are tricky. So hopefully you were able to try some of them. Like I said on the video yesterday, the plan is we're still on schedule for this week. So I'll go over some of these, help you through some of these today. Tomorrow we're going to do the Tootsie Pop activity. So working with related rates. And then Thursday will be a review day and Friday will be the test is the plan. I put some notes. These are the notes. Those are the notes that we took last year with the other textbook, but they're the same. So it's just more examples to look at. So I'm just going to kind of go through the packet ones and kind of help you get started on ones that you had trouble with. Ones you had trouble with on the packet. 2? Yeah, let's look at 2. If I look at 2, we have so these are tricky, but if you go, I didn't get you one. These are the notes from last year over related rates. Okay, 2. Let's look at 2. So it says on 2, sand falling from a chute forms a conical pile where the height is always equal to 4/3 the radius of the base. How fast is the volume changing when the radius of the base is 3 feet and increasing at a rate of 3 inches per minute? So I would definitely have yours out looking at it, reading it. First thing I want to do as I go through these steps, okay, those 4 steps I gave you, that's a good way to get started. So don't get overwhelmed with the wording and all the information they give you. Go through the 4 steps and kind of go from there. So the first thing I look at is I want to know what is given and what is unknown. So as I look at number 2 from the packet, what am I looking for? Anytime I'm looking at a story problem, I always kind of look for what they're looking for first. So what am I looking for? Volume. How fast the volume is changing in relation to the radius. So if anything, it doesn't say a rate. So anytime I'm changing with relation to something else, that is going to be a related rate. 2 rates are related. That's how things are changing. So if I want the radius, how fast the volume is changing when the radius compared to the radius. So I'm looking for dV over dr. That's what I'm looking for. I'm looking for what is the rate that the volume is changing compared to the radius. Okay? Now let's look at what information they give me. As I go through it, I want to know how fast is the volume changing when the radius is 3. So they tell me the radius is 3. Now be careful. As you read it, it says the radius of the base is 3. They give me that. That's the given. That's not changing. That just says I want to know the volume, how the volume is changing when r is 3. So that r equals 3, we're going to wait till after we take the derivative and plug it in because it's a constant. Now, what else? What other information do they give me? That's the unknown, dV over dr. And what do they give me? Do what? They give me the formula for the height, so I can jot that down. H is 4/3 r. Okay. Step 2 is where we really worry about the formula, so I'm going to kind of hold off on the formulas for a second. Step 1 is the known, what they tell me, and what is given. So as I look at this, what do they tell me? What is increasing at a rate of 3 inches per minute? The radius is increasing at a rate. So anytime, like I said yesterday, if I'm dealing with the rate, that is always the derivative. So it is increasing at a rate of 3 inches per minute. And if you notice, it's inches per minute. So that's going to be the radius over time. Inches deals with the radius, minute deals with the time. So that is dr over dt, and that is going to be what? As you read it, they tell me that. Yep, 3 inches per minute. Positive or negative? Positive. It's increasing at a rate. Rate is always derivative. 3 inches per minute. She's not here today? Of course not. Thanks. Okay, so that's the first thing. Look at what they're given. Look at what I'm asking for. I'm looking for the volume. The second part is to come up with an equation that relates volume and radius. So look at your unknown and your given. The second part is come up with the formula relating them. So as I think about this, what's kind of the only formula I know about, I'm dealing with, it's forming a conical pile. So I'm dealing with the cone. So what's really the only formula I know for a cone? Which is what? Yep, 4/3 pi r squared h. So the second step is to come up with the formula. They usually don't give it to you. So we looked at some examples yesterday where we dealt with Pythagorean theorem, area of a circle, volume of a circle, of a sphere. We did the trig, the tangent one. So the second step is to come up with the formula that relates the given dr over dt. Is it 1/3? Yeah, it's 1/3. Sorry, 1/3. 1/3. 1/3 pi r squared h. Yep. Okay, now as I look at this, I want to come up with a formula that relates volume and radius, because that's my given and my unknown. Now if I look at this formula, what issue do I run into? So the second part was to come up with the formula that relates the volume and the radius. As I look at this formula, what issue do I see? I want a formula that just relates the given and the unknown. So the formula, or the volume and the radius. So what issue do I see here? Or think about it this way. I'm going to have to take the derivative in step 3. So as I look at this, h. I have h in there. So I need a formula that just relates volume and radius. I have this random h in here. So what can I do with this h to get it in terms of r? Plug in 4/3 r. So that was step 2. I need to get a formula that just relates my given and unknown. So I want to know my change of the volume, and I want to know the change of the radius. Or I give you the change in the radius. So I need a formula that only relates volume and radius. I cannot keep h in there because do they tell me anything about h? Do they tell me when the height is this? No. So they don't tell me any specific information about h, so I have to get it all in terms of r. So if I simplify this a little bit, volume equals 4/9 pi r cubed. That's step 2. So now I have a formula that relates my given and unknown. Volume, radius. Third step is what? Take the derivative. So when I take the derivative of v, that's dv over dr. Because r is inside here, so it's dv over dr because it's in terms of r. When I take the derivative of this, don't be worried about the pi, so it's not necessarily product rule because the pi is just a constant. So it's not like having an x there. We have to do a product rule. So what would be the derivative of 4/9 pi r cubed? Okay. Bring the 3 out front. So that'd be 12/9, which would reduce to 4/3. So that's 4/3 pi r squared. And what do I have to put at the end? dr over dt. Because the radius is in relation to time. Fourth step, look at what they give you. If I want to know dv dr, I need to be able to plug numbers in for everything else. So what do I plug in for r? What do I plug in for dr dt? So plug in your 3, plug in dr dt. Now let's see. What did I have? Just a second. Be careful. As I look at this, easy mistake to make. My volume, read the volume. The volume is changing when the radius of the base is what? Nope. 3 feet. So they tell you the radius is 3 feet. They tell you I want to know the radius is increasing at a rate of 3 inches per minute. So they have to be the same measure. So if this is 3 inches per minute, what is that really in feet? Fourth, 0.25. So that's really 0.25 feet per minute. So be careful because it was 2 different measurements. The radius they give you is in feet. They tell you it's increasing at 3 inches per minute, so that also has to be in feet. So 3 inches is 0.25. So when you plug it in, make sure you plug in a 3 for r and a 0.25 for your dr dt. Be careful with that. Okay, and then that should be able to get you started with that. I'm not going to go through and finish it. Okay, a couple other ones I'll do with you in the other preferences. And just as you will see these over and over and over and over again. So if you don't put in the time to kind of get through them now, it's going to not be good. The other ones. Okay, let's look at 9. So go ahead and turn to 9 real quick. Let me kind of get started in 9 with you. So let's look at 9. 9's a tricky one. Please try to get these done. Get as much done tonight as you can. We won't have a ton of time tomorrow to go over questions, but that way you can still come in. I'll be here after school till about 3:45 today, and I'll be here before school tomorrow. I can be here after school a little bit if you need me. So please ask before it gets too far down the road. Okay, let's look at 9. So as I go through 9, let's read 9. Let me get another copy real quick so I can read off of it. So as I read 9, the first thing I'm thinking, we did one kind of similar to it in the notes yesterday, but as I read 9, I'm going to want to draw a picture. There's lots of stuff going on, planes flying around. So let's draw a picture for number 9. Or the number 9 is ships. So as I look at 9, it says ship A is 15 miles east of P and moving west at 20 miles per hour. Ship B is 60 miles south of P and moving north at 15 miles per hour. At what rate is the distance between them changing after 1 hour? Is the distance increasing or decreasing? So as I read this, it's going to be asking for something. So I want to know at what rate the distance between them is changing after 1 hour. So let's draw a picture for this and see if we can kind of make sense. Ship A is moving 15 miles east of P and is moving west at. So ship A. So let's draw a picture. Here's P. Ship A is 15 miles east of P. Because it says ship A is 15 miles east of P and is moving west at 15, let's see, first of all, ship A is 15 miles east of P, so I know this is 15. They tell me that measurement is 15 miles away. And I'm going to go ahead and label that as A. So that's going to be side A, just because I'm going to label it. Doesn't really matter what you label it, but And it's moving west at 20 miles per hour. So I talked about yesterday in the notes, if I do speed, miles per hour, speed is always a what? Rate. So as I look at the rate of A, it is 20 miles per hour. So that rate is what? How would I label that? It's a derivative because it's a rate. Speed is always a rate, so speed is always just derivative. So how would I label that derivative? It's what over what? dA over, it's inches per minute. So is the distance in inches, which is A, over what? Inches per minute. So it's the change in the distance, which is A, over the change in what? Time, dt. Inches per minute. Distance over time, inches per minute. And that is 20 miles per hour. And if I'm moving left, that's going to be a negative 20 miles per hour. So my rate for that ship as it moves west, it's moving left. So think about a coordinate plane, it's moving left, so that's a negative. Now, it also tells me I have ship B, which is 60 miles south. So I'm going to move it, put it a little further down. It's 60 miles south of P. So if I label this as side B, has a distance of 60. So that's just 60 miles. And that is moving at a rate, north at a rate of what? 15, and that is going to be dB over dt, because it's miles per hour. B was the distance in miles, so that is miles per hour, dB over dt. And I'm going up, so that's a positive 15. Now what I want to know, as I look at this picture, what does it look like I have? Triangle. And I'm going to go ahead and label this as C. And as I read this, what are they asking for? They're always going to be asking for a rate. So what rate are they asking for in 9? Do what? Right, but a little more specific. If I look at the picture, I want the, at what rate is the what changing? The distance between them. So what do I have labeled as the distance between them? C. So how would I, if I want to know how the distance is changing, I'm looking for dc over dt. That's what I'm looking for. I want to know at what rate derivative, at what rate is the distance between them, which is the c, changing. Now as I just look at this, we can answer the next question. If A is moving left and B is moving north, the distance between them is going to be what? Increasing or decreasing? Decreasing. This is A is moving left, B is moving north, so the distance between them is going to get smaller because they're both going to point B. So I'm expecting that dc over dt will be negative because it should be decreasing. The distance between them should be decreasing, which kind of makes sense if you think about the picture. Now, as I look at this is kind of the first part. The first part is to look at this and kind of identify what I have here. Now, as I go through and look at this, we have, now, I made a mistake here. This shouldn't be a positive 15. I misspoke here. What's happening to the distance? If this is moving north, what's happening to the distance between B and P? It's decreasing. This should be negative. Sorry, I explained that crappy. This is the rate at which the distance is decreasing. If I start here and I'm going north, the distance between these two is going to be getting smaller. Same reason for this one. If I start at A and go left, the distance between them is decreasing, so it's a negative. So these both should be a negative. Sorry, I explained that really bad. Does that make sense? So the distance between P and A and P and B are getting smaller because I'm going towards P. So this was the first part. This was all the first part. Draw a picture, label the parts, blah, blah, blah. The second part I am dealing with is creating a formula that relates all this crap together. So if I look at a formula, my first thought, formula that relates all this, don't make it harder than it is. Yeah, I have a right triangle. So even though there's lots of stuff going on and it's confusing, when I look to come up with the formula, I want to relate sides A, B, and C. Pythagorean theorem. So A squared plus B squared equals C squared. Now, as I go through and look at this, we need to have, let's see here, we need to be able to plug in, let's see. So as I look at my distance here, let's think about this. A and B. So A is the distance that I am, the distance between P and A. It's not a constant. So if I think about this, what distance do I start with? So if I look at A, what distance do I start with? I'm going towards P, so it is decreasing, but A is the distance. So what distance do I start with? I'm moving left, I'm moving west. So what distance do I start with? 15. I start with 15 because A is the distance. So I want to know the distance after so much time has passed. So it's going to start with 15. I'm moving west at negative 20 miles per hour. Now if I think about this, this is going to be X. X is going to represent how far I am after an hour. So it's going to be 15 minus how far I go after an hour. Now if I look at B, it's going to be the same way. B, what distance do I start with? 60 minus however far I go after I go an hour, because it's the distance after an hour. So I want to know how far away I am after an hour. So I start with 15 and then I minus however far I go after an hour. So there's my formula. Let's go ahead and take the derivative, see what I have here. So we're going to have 2 in front, 15 minus x. We're going to have the chain rule. Now if I take this derivative, if I do the chain rule, this is going to be a what? Negative 1. So this will be a negative dx dt. It's like we did yesterday. When I take the derivative of something, I put dx dt next to it. Plus 260 minus x squared negative dx dt equals 2c dc dt. So they kind of go through and take the derivative. Now as I go through and look at this, we have 2. Now I can start plugging in. Step 3 is to start plugging in. Actually, I'm off. Step 3 was the derivative. Step 4 was to plug in, I believe. So as I plug in, now let's think about this. What's going to be x? X is the distance I go after an hour. So as I'm looking at this top part here, I go 20 miles an hour. So I want to know how close they are after an hour. So how far do I go after an hour? If I go 20 miles an hour, I went 20. So it's going to be minus 20. Now let's think about this. I want to know the distance between them after an hour. So X is going to be the distance that ship A goes after an hour. I go 20 miles per hour. So after an hour, I've went 20 miles. dx dt is going to be the negative 20. Now I have two negatives here. You really only need one. It's kind of a double whatever. I know it's negative, so that's a negative 20. Plus 2 times 60 minus x is the distance. Part B, boat B is wet. So how fast is boat B traveling per hour? 15 miles per hour. So x is going to be, how far has it went in 1 hour? It goes 15 miles an hour, 15. dx dt, the rate of that is 15. And that's a negative. dx dt equals 2. Do I know anything about C? And dc dt is what I'm looking for. I'm looking for dc dt. But I don't know anything about C. So this is kind of like we did yesterday in the notes. I know nothing about C. They don't tell me that. But I know I need to plug something in for C because I need to solve this for dc dt. So as I look at C, we can go ahead and create a triangle. So if I think about creating a triangle here, whatever we have here, this is going to be the distance after, see where I'm at. Okay. So if I do Pythagorean theorem, let's just think about it. I want to find C. So let's think about it. This is a squared plus b squared. Now we're talking about the length after the hour. So what is A going to be? I guess we don't have to draw another picture. What is A going to be after an hour? If A started at 15, I go 20 miles to the west, what position am I going to be at if I start at 15, positive 15, and go 20 miles to the west? I'm going to be at what? Negative 5. So A is negative 5. So that is the distance or the length after an hour. Plus B, what's going to be the distance or B after an hour? If I start at 60 south, and it's 15 miles an hour, I go 15 miles an hour north. So after an hour, I'm going to be at, start at 60, I'm going north, I go 15 miles an hour, 45. Okay, so use this to find C, get a decimal answer. Once you find C, plug it in, and then you should be able to solve for dc dt. That's one of the trickiest ones, but I at least want to go through it with you. So at least you probably won't see one this hard again in this class, but just so you at least kind of get used to looking at it, kind of thinking about it. Okay. So find C on there, plug it in, and then you can solve that whole equation for dc dt. Any other ones? Let's look at 11. Let's look at 11 real quick. I'll get you started on 11. Okay, let's look at 11. Has a picture drawn for you already. Let's see. An aircraft is flying horizontally at a constant height of 4,000 feet above a fixed observation point B, kind of similar to the one we did yesterday in the notes. At a certain instant, the angle of elevation theta is 30 degrees and decreasing, and the speed of the craft is 300 miles per hour. Think about it. The picture makes sense. If I have a plane and it is traveling, here's my angle of elevation. As this plane goes this way, this angle of elevation is going to be getting smaller. So as this plane goes this way, this elevation is going to be getting smaller. Does that kind of make sense? So whenever I'm looking for d theta dt, I'm going to be expecting that to be negative because it should be decreasing. So as the plane goes, that angle of elevation is going to be getting smaller. Okay. So as I look at my picture, I'm just going to redraw it real quick. Here's my picture. The elevation is 4,000. So like I said yesterday on the example, elevation is always that constant. So it's going to be a constant of 4,000. Let's label this as x because it's horizontal, and let's just label this as z. It doesn't really matter what you label them. I always do horizontal x, vertical y, hypotenuse. I usually pick c or z or whatever. It doesn't really matter. And this is theta. So part A, there's two parts to this question. Part A, I want to know how fast is theta decreasing at this instant. So what do I want to know? I want to know how fast theta is decreasing. So if I write it with derivatives, that's going to be what? I want to know how fast theta is decreasing. So it's going to be what over what? D theta, the change in theta, over the change in what? It's how my angle is changing when compared to what? Time, dt. So I want to know how my angle is decreasing as time goes by. So d theta over dt. That's what I want to know. So now we're going to look at what is given to us. So I have that the speed of the aircraft is what? Do what? 300 miles an hour. So speed is, that's a crappy aircraft, but that's okay. Speed is always a rate. Now as I look at my picture, speed is always a rate. So that's going to be where you get your other derivative from. Like I said yesterday on the notes, speed is always talking about what part of this triangle. When I think about the speed of an airplane, I want to know the distance it's traveled compared to time. So what part of this, or what side of this triangle, will give me the actual distance that is traveled? X. So dx dt is going to be 300, and that's miles per hour. Like I said, whenever I do speed, it's always the horizontal distance. So that is the distance I've traveled compared to time. So that's going to be x. So dx over dt, they tell me that is my other rate, 300 miles per hour, because that is a speed. Now as I look at this 4,000 is in what? Feet. So what do I want to get it into? This is miles per hour. So I want to get it to, yes, miles per, or feet per, let's see. I'm trying to think why. If you look at your answer, okay, I think that you want it in feet per second because I think usually we measure angle something per second. So if an angle is decreasing, we usually measure it per second. So I think that's why you want it in seconds. So anytime you're talking about that, I think they usually want it in seconds. I'm not really sure. I'll be more specific if I tell you what to convert it to. So we want to get it to feet per second. So we think conversions. Okay, I want to try to get feet on top. So I have miles on the bottom. I want to try to cancel out. So how many feet are in 1 mile? If I did this in the science class, conversion. I want to cancel out the miles, so I want to put miles on the bottom. So how many feet per 1 mile? 5,280. So that will get me, my miles will cancel, so that will get me feet on the top. Now I need to get seconds on the bottom. So I want to put hours on top, so the hours will cancel. So how many seconds are in 1 hour? 3,600. How many seconds are in a minute? 60. How many minutes in an hour? 60. So 60 times 60, 3,600. So if you go through and simplify this, this will give you, if you use a calculator, 440 feet per second. So that is dx/dt. So make sure it's all in the same measurement. This 4,000 was given to me in feet, so I want to convert this 300 to feet per second. Now as I go through the second part, this is all the first part. The second part is create a formula that relates everything that is given to you. I want to relate theta. I give you the angle opposite, and I give you x. I don't give you anything about z. I can tell you nothing about the hypotenuse. So if I give you theta, I tell you stuff about x. I know y is 4,000. So what formula will I use to relate theta, 4,000, and x? Tangent. So tangent of theta is going to be what over what? No, because that's a rate. So we don't use that until we take the derivative. 4,000, that's a given, so that's not changing. So it's 4,000 over x. Like we did yesterday. Now as I look at this, I'm thinking part 4 is to take the derivative. So as I try to take the derivative of this, you could do it. What would be an easier way to rewrite this that would make taking the derivative a lot easier? You could do it that way. What different trig function could I rewrite this? Instead of tangent theta equals 4,000 over x, what if I did cotangent theta? What would cotangent theta be? So what's tangent is y over opposite over adjacent. Cotangent is adjacent over opposite. So that would give me x over 4,000. And this would be a little easier to take the derivative of because I can just write it like that. Doesn't really matter. You could have done the negative up top and then do the tangent. It doesn't really matter. But if I just rewrite it as cotangent instead, that will put the 4,000 on the bottom, so I can rewrite it as 1 over 4,000 times x, which will be a lot easier when I take the derivative. So I don't do anything with the dx dt because that is the derivative. So I plug that in until after I take the derivative. Now let's take the derivative of this. Derivative of cotangent theta. We want to have it memorized by the end of the week. Negative cosecant squared theta. D theta over dt, because I took the derivative, equals derivative of 1 over 4,000 x. One over 4,000 what? Dx dt. So that was step 3, take the derivative. Step 4, plug in what you know. I am looking for d theta dt, so I should be able to plug stuff in for theta dx dt. So as I look at this, I should be able to plug stuff in, so I just have d theta dt left. I know dx dt I found up here, that's my 440. I know d theta dt is what I'm looking for, so it's going to stay there. Theta, I need to find theta. We kind of did this yesterday, so how do I find theta? I need to be able to plug theta in, so I just have d theta dt left. Don't make it harder, read it. Theta is what? Hmm? 30 degrees. And it wants it in, does it say what it wanted in? It wants it in radians per second. I don't know why they assume that that's what you want, but they'll tell you. So if 30 degrees in radians is pi over 6. So pi over 6. I want to know d theta dt, so that's going to stay my variable. 1 over 4,000. dx dt is 440. So go through, and you should be able to plug stuff in, or solve this for d theta dt. Any questions on that? I'm trying to do some of the trickier ones with you. The other ones you can find stuff in your notes. But now part B, I want to know how fast is the distance between the aircraft and the observation point changing at this instant. So if I look at part B, it's going to be a little different. What related rate am I looking for part B? I want to know how fast the distance between the aircraft and the observation point is changing. So I'm looking for what? Do what? Yeah. So what, as I'm looking at this, I want to know the distance between my observation, which is down here, and the aircraft. I want to know how it's changing. So I'm looking for not d theta, because I want to look. I'm looking how the distance is changing between the observation point and the airplane. So what represents the distance between the observation point and the airplane? dz. So I'm looking for part B, I'm looking for dz over dt. Now as I look at this, I'm not going to go through all this with you, but as I look at this, what formula am I going to use for this? Now I'm looking for the distance, so I don't care about the angle anymore. I care about the distance, or I care about the sides. So now I'm going to use the Pythagorean theorem to kind of go through and help me solve dz dt. I don't care about an angle, so since I'm not worried about an angle, that's why I don't use the trig function. Now I worry about the side length, how the side length is changing, so we're going to use Pythagorean theorem to finish it from there. Okay, any other questions? Okay, that should kind of get you started on the rest of those. Those are definitely the trickiest ones. Let me get you started on 12 real quick, and then I'll give you some time to work on these. Let's look at 12. So if I look at 12, a beacon that makes one revolution every 10 seconds is located on a ship anchored 4 kilometers from a straight shoreline. Let's draw a picture. Here's my straight shoreline. I have a beacon that is on a ship anchored 4 kilometers from a straight shoreline. So here's my 4 kilometers, that's straight out. So I know this is 90, it doesn't look like it, but that's straight out. Here's my beacon. It's a nice light. On a ship 4 kilometers out. And I want to know how fast the beam is moving along the shoreline when it makes an angle of 45 degrees with the shore. So if I think about a picture, what will my picture look like if I want to know how fast the beam is moving along the shoreline? So if I think about a beam shooting out here, If I want to know how fast it's moving across the shoreline, what kind of picture am I going to draw? Down. I'm going to have a triangle. I want to know the distance it's moving across the shoreline. So if I think about this triangle, that's my beam. I'm going to be worried about, this is x. I label that x. I want to know how that distance is changing. So I'm looking for dx dt. That's what they're asking for. I want to know how that distance is changing, so that's going to be dx dt. Because I want to know how the distance on the shoreline is changing, how it moves across the shoreline. What information do they tell me? What was it? The angle with the shore. So what angle here is going to be the angle the beam makes with the shore? Actually right here. This is the angle, theta. So that is the angle it makes with the shore. So that's going to be my theta. And they tell me theta is 45 degrees. Now be careful, that's not a related rate because it just tells me the angle they make. Now as I think about this, this is tricky to come up with. D theta over dt. This is how my angle is moving in relation to time. Now they don't specifically say this, but they tell me that it moves 10 seconds. It's one revolution per 10 seconds. 10 seconds. So that's going to tell you kind of how fast it's moving. It's going to tell you d theta dt, or how my angle is changing, because I know it does one full rotation after 10 seconds. So kind of weird to get to it, but that actually tells you how your angle is changing, because that tells you how fast it's moving. Okay, I want to know I want it in radians per second, because we always want to deal with theta in radians per second. So I need to get rid of revolutions. So I'm going to put revolutions on the bottom. I want to try to get to radians on top and seconds on the bottom. So how many radians are in one revolution? 2 pi. So 2 pi radians. So that will get me radians on top. My revolutions will cancel. That will give me radians on top. So I'll go with the top part. And I want radians per second. And we already have second in the denominator. So it's just going to be pi over 5 radians per second. So that is how I get my d theta dt, which is a stretch. I get it. Like I said, I'm doing some of the harder ones with you, getting it started. The other ones I think you can kind of figure out from the information they give you. Now, as I look at my picture, I want to get a formula that relates everything I'm given. I'm given theta, angle is 45, which in radians will be, do they give me? What does they tell me? Theta is 45 degrees. I think I want that in radians. That's weird. Okay. Which 45 degrees in radians is pi over 4. Is that right? I think so. Okay. We'll look at that in a second. That's okay. Anyway. So as I look at this, that's pi over 4. So what formula, if I look at my picture, I'm dealing with angle. So anytime you're dealing with angles, I think one of the trig ones. So what trig one will I have relating this angle, x, and 4? Tangent. So tangent of theta is what? X over 4. Now the constants in the denominator, which is good, so I don't have to switch it to cotangent like the one I did before it. So if I take the derivative of tangent, secant squared, d theta dt. If I take the derivative of x over 4, that's going to be what? Mm-hmm. 1/4 dx dt. Now I want to know d theta, or I want to know dx dt, so I should be able to plug stuff in for everything else. Secant squared, what do they tell me theta is? Pi over 4. D theta dt is pi over 5. 1/4 dx dt. So you can solve that equation and find out dx dt. Okay? So like I said, those are definitely the trickiest ones out of these. So that should help you get started with these. Look at examples. Some of the examples are very similar to the ones they give you. So hopefully that helps. Okay? So like I said, you have about 15 minutes or 20 minutes. I would work on this as you kind of go through this. This helps you get started on some of the tricky ones. Real quick, I noticed this when I was checking the homework. Okay, just look, or the homework quiz. I'm not going to pass the homework quiz back yet because you still need to take it. But as I look at this one, I realized as I taught it last week, I did it wrong. Which as I was teaching it, as I was going over it in the homework, I'll just do it on the board so Kaylee can see this. As I was doing it, going over it on the homework, I was like, this isn't right, but apparently I was too lazy to figure it out. So this one, 36, I forget which one it was on. It's when you had to do the product rule with 3 functions. Now, if you wrote down the answer I did on the board, I didn't count it off because I obviously did it wrong. Okay, if you have to do the product rule with 3 functions right next to each other, how you have to do this is you have to think about it, because the product rule is first times the derivative of the second plus second times the derivative of the first. What I did was I went through and distributed, or I took the derivative of the first 2 and then took that derivative into the product rule. That doesn't make sense. I don't know why I didn't stop myself when I was explaining this. So what you have to do, if you have the product rule of 3 functions, you take the derivative of the first, keep the other 2 the same, so how you take the derivative of 3 functions, you take the derivative of the first, keep the other 2 the same. So basically you're using the same property because the product rule is first times the derivative of the second. So all you're doing is you're taking the derivative of 1, keeping the other 2 the same. Adding that to 1.
Keep the other 2 the same. So as I go through it, we're using the product rule, but you just take the derivative of one of the functions, keep the other 2 the same, plus take the derivative of the middle function, keep the outside 2 the same, plus take the derivative of the last function and keep the first 2 the same, which is 2x plus 1. So that is how you take the derivative of 3. I said it wrong. I taught it wrong, or ran it over homework. And it happened to be on the homework quiz, so I don't count it off if you did it the way I told you. But this is the way you do the product of 3 functions. You take derivative of 1, keep the other 2 the same, plus take the derivative of another 1, keep the other 2 the same, plus take the derivative of the last one, keep the other 2 the same, and go through and simplify that. So that is my bad. I just wanted to make sure I pointed that out. Okay. So go ahead and keep working on the related rates. I only gave you 12 problems for a reason.